So welcome everyone to the next episode of our Coffee Breakdown podcast. Today we have as our guest Simon van Mulders. He did his PhD thesis at EPFL on model-based optimization of a tokamak, and he's currently at ITER working on state estimation. So welcome, Simon, to the podcast.
Hello, Adam. Thanks for inviting me.
Yeah, no problem. And I think those beginning few words were a bit of a mouthful for our listeners, so we'll slowly get through all of it, hopefully, during this discussion. But the first question to you is, well, why do we need to optimize our tokamak, and what are we exactly optimizing?
Okay, yeah, so let's try to start from the basics of what we are trying to do here. So we are working with tokamaks in which we confine a plasma with the aim of achieving nuclear fusion and in the end achieving net energy production for from these fusion reactions which happen in the plasma. So when we try to formulate this as an optimization problem, we need a cost function and a constraint function of like cost function, like what it is we're optimizing. And we can say we want to optimize the performance, but how do we describe this performance? In the case of fusion energy production, what we want to optimize inside the plasma really is a triple product of three variables. This is a triple product of the density of the plasma, the temperature of the plasma, and the confinement time. Confinement time is basically a metric of how well the plasma is behaving as a thermal insulator. And so the better we can confine the heat inside the plasma, the more fusion energy production we can achieve. Another thing we can optimize is the pulse duration. So for the magnetic geometry that we need inside the tokamak, we need actually to run a plasma current through the plasma itself. So the plasma will be carrying a current. And this current has to be maintained throughout the entire pulse duration. And the way this is basically done is by a transformer effect. So in the middle of, so the tokamak is like a donut shape, in which the plasma is basically floating. And in the center of the tokamak, there is a central solenoid in which a current in this coil is ramped up, and the changing magnetic flux in time induces a current inside the plasma. Now, this current inside the plasma can also be generated by alternative mechanisms. One of them is auxiliary current drive. So we can use the same kind of devices that we use to heat the plasma can also be used to drive current in the plasma. But of course, this is expensive because we want to inject as little power as possible in able to be able to achieve a net fusion gain. And so there is an extra mechanism that we get basically for free, which is a self-generated current inside the plasma called bootstrap current. And this bootstrap current, which is basically present whenever we have a pressure gradient, is something we want to maximize. So this is another performance metric on top of the earlier ones I mentioned. So to basically to enable us to extend the pulse duration as long as possible. So that's examples of what we can be optimizing, so the cost functions. But at the same time, we need to take some constraints into account. So basically, we need to avoid disruptions. Disruption is like a sudden loss of the energy and of the current inside the plasma. So basically, you can imagine the plasma bumping into the wall, and because of the extreme temperatures and the extreme energy content of the plasma, this is of course a very bad event that we have to avoid for sure once we are talking about a reactor where we want a reliable operation, where we don't want to destroy the reactor wall, obviously. And other constraints are just technical limits. We have limits, for example, on the power supplies to our coils, which limit how fast we can ramp up a current in the central solenoid or in any of the other coils that are used to shape the plasma, things like this. So that's the basic framework of optimization for a tokamak.
Yeah, great. And it seems that there's a lot of factors that you have to take into account in this optimization. It seems that from a cost perspective, all your parameters are global parameters. They're sort of just numbers that represent the plasma as a whole. And I'm curious how well you can describe a plasma using those numbers. Is it sufficient, or are there many solutions that give effectively the same set of numbers, right?
Yeah, so the answer to this question is no, it's not sufficient. You cannot just describe the plasma with a number of bulk parameters. You need to look into the distribution of quantities inside the plasma. I can give an example of this, which is very important in the context of a tokamak, which is the safety factor. So the safety factor is basically related to the distribution of the plasma current inside the plasma. And it's also a metric for the local pitch angle of the magnetic field. So it's basically it gives a metric for how much poloidal field, so field in the poloidal direction you have with respect to magnetic field in the toroidal direction, which is in the along the axis of the donut, let's say. And so this safety factor, so first of all, why is it called safety factor? It's called safety factor because the value of this safety factor profile or Q profile at the edge of the plasma has to be maintained high enough, usually above, usually at least above 3. The reason for this is that the safety factor by the edge is basically inversely proportional to the total plasma current inside the plasma. And for a given magnetic field, for a given toroidal magnetic field, we can increase the plasma current only up to a certain value. If you would increase it further than that, we get what we call an external kink instability, and basically the plasma will kink out and disrupt. So that's why in the early years of tokamak research, people call this safety factor. But it turns out that this safety factor profile has many more constraints linked to it. And one of them is what we called tearing modes or neoclassical tearing modes. I will not go into the details of the physics, but basically under normal operation in a tokamak, you have a set of nested flux surfaces. So if you have the magnetic axis in the center where your temperature is highest, and then it's surrounded, it's like an onion, it's surrounded by sets of magnetic flux surfaces on which the magnetic flux is constant. That's why they are called like this. And on these flux surfaces, you also have constant temperature and density. And basically, when you get a tearing mode, this nested geometry is broken. And because of locally breaking this nested geometry, you get a larger transport of heat. So you get a local flattening in your temperature profile, and this is very bad for performance. Even worse, it can trigger disruption. And now I come to the link with the safety factor profile. The conditions under which you can trigger such a tearing mode are often linked to the safety factor profile. First of all, they appear at rational surfaces of this Q profile, Q equals 2, Q equals 1.5. And so one thing we can introduce as a constraint in our optimization is the local conditions at these rational surfaces as to avoid these tearing modes. That's one example. Another example is linked to the control of the position of the plasma. So basically, when we start to elongate the shape of a plasma, the vertical position of the plasma can become unstable, or actually by definition becomes unstable and requires control. real-time control with the colloidal field coils. Now, this has been done since the early days of tokamak research, but the catch is that if the current density inside the plasma becomes too peaked, so if there's too little current by the edge of the plasma, it becomes very hard to control the position of the plasma. So this is another example where the current distribution, so a distributed quantity, is important for taking into account the constraints on operations.
Yeah, that's actually very interesting, because then in the sense of not just the optimization part, but the estimation of the state, you need to have a lot of diagnostics in order to figure out, well, what exactly is this distribution inside this plasma? And I imagine that's not always very straightforward to get from a diagnostic. So how do you balance that, what you can measure versus what you need to know?
Yeah, so as you can imagine, a plasma is a challenging environment to make measurements. So of course, it's you can make very little measurements inside the plasma itself, and so most of the measurements rely on like what can be seen like from around the vacuum vessel, let's say. So for example, to measure temperature, you can like shoot a laser through the plasma, and based on the scattered light, get estimates of the temperature. Now for the Q profile, or the safety factor profile, or plasma current distribution, these quantities are all like closely related to each other. You are actually what you can do is look at the you have a set of magnetic probes around a tokamak, which measure just outside of or inside the vacuum vessel the local values of the magnetic field. And by combining these measurements and combining them with a model of the force balance inside the plasma, you can basically solve a least square fit of how which magnetic geometry of my plasma that is a solution of this pressure balance best fits the magnetic measurements that I observe. But even doing this, it is not obvious to get a good estimate of this Q profile, because the plasma shields basically the internal distribution of plasma current from the magnetic probes that are far away from the plasma. They have only little sensitivity to what is happening deep inside the plasma. So there are many solutions of the current distribution there that would fit the same measurements and fit this pressure balance equation. And
right.
So, yeah.
So even in that case where you have sort of in some measurements to kind of guide you towards some constraints for the plasma state, one, it's clear to me that you need some sort of model in order to estimate, well, what plasma state it could be in. But even then, the result of the model is just a solution from a family of solutions, is what you're saying. Okay. And that's very interesting, because then how, like in the essence of, I suppose, your work, where you then use this combination of measurements and model predictions to do optimization, how does that play out, right? Like how do you account for this family of solutions?
Yeah, so one thing we can do here is, so when the measurements are not enough to properly constrain the solution of what we want to observe, we can add extra models to the reconstruction problem. So basically what we can do is include a model for current diffusion, and combine in a way the modeling and the measurements into a best estimate for the plasma state. This can be done with a technique that is called Kalman filtering. And so basically the idea is that you you have a model for the time dynamics, which can be nonlinear. In the case it's nonlinear, it's called an extended Kalman filter, but the principle is basically the same. So you have a model for the time dynamics, and you assume that you have some uncertainty in your model, and this is quantified with the process noise covariance matrix. It's a difficult word, but basically means you have some noise that is added to your state while you evolve your state in your model, and the bigger this noise is, the less you trust your model. At the same time, you can have a model for your diagnostics, and on these measurements you have a certain amount of measurement noise, and you have a second covariance matrix there describing the noise on your measurements. And basically by making a trade-off between these two, so based on how much you trust your model versus how much you trust your measurement, you can get an estimate of the plasma state that combines these two. So basically you evolve the dynamics, which are like a partial differential equation. In the case of the Q profile, it's this current diffusion equation. And every time step that you evolve the model, you make a correction based on the measurements. And so in this way, it can actually be proven that in the case of Gaussian noise, this gives you an optimal estimate at every time step of, in this case, the Q profile.
Wow, okay. And so but then this model evaluation, I mean, in the sense of online state estimation, has to be incredibly fast. I mean, I'm not sure if you are in the moment doing work towards online estimation, but even offline, I imagine there's so much iteration and so many models you have to evaluate and a lot of computation happening that there are strict limitations on what types of models you can use inside such an algorithm. So can you speak a little bit about that?
That's exactly true. So this is of interest both in real time. So during the plasma discharge, we need feedback controllers and that are aware of the plasma state. So there we need a fast model, but also even after discharge, we need models that are fast enough so that we can get the reconstruction in a reasonable time scale, like to see so that we are aware what happened inside the plasma. Now, for this, there is a family of models that have been derived. Usually, we call these kind of models control-oriented models. So in the fusion community, there is a whole hierarchy of models which go from very computationally expensive. Usually, the models that dig into the turbulent transport, they have to model extremely complex phenomena, often in 5 dimensions, and this is extremely computationally expensive. Like you said, for real-time purposes or even for post-discharge analysis purposes, we need faster models. So in my case, during my PhD, I worked with a model that is called RAPTOR, which stands for Rapid Plasma Transport Simulator, and it basically solves a set of partial differential equations for the transport of heat, particles, and current density. To be able to be fast enough, it needs to make use of reduced models for, on the one hand, the evaluation of heat sources and current drive sources, and on the other hand, for turbulent transport. Because, like I said, turbulent transport models are very slow, but inside the heat diffusion equation, you need to evaluate the local level of diffusivity, which is governed by this turbulent transport. And there are a few options that we can use for a control-oriented model. So one of them is we can use a simple model where we use basically an analytical formula of how is the local diffusivity dependent on global plasma parameters like temperature, Q profile, like it can be nonlinearly dependent on the state itself. And this model we have some tuning parameters, and these we can tune against experimental data. So here you'll immediately see the limitation of this. You need to have experimental data. So if you want to start optimizing scenarios of future machines, you cannot do this. This is very interesting. If you have a given scenario on a tokamak, you have a lot of experimental data to train on, you tune these coefficients, and then you can predict what is going to happen in the next discharge fairly well. A second approach is a scaling law approach. So this diffusivity based on measurements in many different tokamaks, you can kind of extrapolate, like make a scaling law fit, and then you can make some predictions. But of course, there is no guarantee that this scaling law will capture all the nonlinear physics that are actually going on inside the tokamak. And then there is a third option that is more recent, which is actually a very interesting one. So these complex turbulence models that are very slow, what I talked about before, one can derive neural network surrogate models of these. So basically the idea is a large database is derived with like a lot of the model outputs of the complex model for a lot of different inputs, and then this input-output mapping of the way the model predicts the turbulent transport, this is fitted with a neural network, and evaluating the neural network is very quick and can be used inside a real-time model. So that's the kind of tricks we use to make models fast enough so we can use them in real time on the real-time control system.
Of course, it's very nice that you mentioned the neural network stuff. As you know, I'm involved in that kind of work. So indeed, that is a very interesting way to go forward in accelerating models, and perhaps not even for turbulence, but for the other components, other models necessary for the optimization process. It could be interesting to look in that route. But I would like to just sort of ask, from your point of view, it's been floated around a bit within the control groups here in the Netherlands, that sometimes it's also beneficial that these fast models have or are able to compute their Jacobians, like basically the derivatives, right? And how does that play into the work that you're doing? Like, what would it improve? Does it improve anything? Is it required? And maybe what can you not do if you don't have them?
Yeah, that's an extremely interesting question, because it's very related to the work I've been doing, because one of the big selling points of Raptor is that we have all the analytical Jacobians available. And this allows you to do different things. So one of them is when we talk about solving an optimization problem. So imagine we formulate an optimization problem of we want to, like, for example, optimize the Q profile to have a given shape that avoids steering modes and minimizes turbulent transport. Now, when we solve this optimization problem, the most efficient way of solving an optimization problem is when you have the gradients of your cost and constraint functions available analytically. Because you can think of it, so you have a set of optimization variables, which are the parameters you want to optimize. This can be at which location you heat the plasma. This can be the value of the plasma current, whatever. So you have a set of optimization variables. And then basically you start with an initial point, so initial guess of these optimization variables. And then the optimization routine will want to make an update to this initial guess that gives you like a lower value of the cost function in case you want to minimize the cost function. And so if you have local gradient information, basically you can evaluate analytically the gradient of this cost function and point towards the steepest descent direction. And so based on this information, you can like very efficiently navigate this optimization space and find the optimum. So for optimization purposes, this is very important, but actually also for control purposes, it can be very important. And one nice example is the linearization. So the dynamics of the plasma, so in this case of the temperature and current density evolution, are governed by a nonlinear set of PDEs. Now, in case we want to do like real-time adjustments of the plasma state, and we want to have real-time information on the dynamics of the plasma, if we have to use the fully nonlinear model of the plasma dynamics, this is going to be very slow, because it's a nonlinear model is more costly to evaluate than a linearized model. But if we can pre-compute a set of linearized models, we can use the linearized dynamics. And now I get into a topic which is called model predictive control. So basically, when we are at a given state, which can be different from the state we wanted to achieve in the plasma, we can make use of these linearized dynamics of the plasma to optimize in real time how do we need to change the actuators, so the heating, whatever we are steering, to steer the plasma state back to the reference trajectory. So these are two examples where linearization where the analytical Jacobians make a big difference and allow you to do very cool stuff that would take forever if you had to, do a finite differencing to find the Jacobians.
Yeah, that's interesting, because the way I guess the physics community pretty much approaches modeling is that some of these equations or systems of equations anyway are so complex and nonlinear that you really cannot pull out the Jacobian from them analytically, and so you're kind of stuck with the requirement from a control or optimization perspective that it would be nice to have, but then from a physics perspective, it's nearly impossible to derive, right? And indeed, this sort of like neural network or even simplified model approach allows you to construct something that you can get the derivatives from. And so, but in the case that you don't have these derivatives, and so you have to resort to finite differences, as you've mentioned, are there limitations to that? What does it prevent you from being able to do? Is it just a matter of now you have a less efficient computation, or can it actually cause whatever control or optimization algorithm to be completely off?
So, well, of course, in the case of real-time control, there is a very clear constraint in the sense you have to be fast enough to be able to be able to do the computation in real time. Now, if you have if you are doing an optimization offline, so not on the real-time control system, in principle, you have it's just going to make the computation slower if you have to calculate the gradient or the Jacobian numerically. But in principle, you can still get to the optimized solution, I would say. Of course, it will, yeah, you will need to take the step with which you do the differencing has to be fine enough to get a good Jacobian, but and your optimization will be much slower. But I guess you can still achieve you can still find the optimum. Yeah.
Okay, and so maybe let's go back to this concept that you put forward of model predictive control. It seems to be an interesting method to sort of address any discrepancies between either a controller or a control environment that you have made and its difference between that and an actual experiment, right? So are there any requirements for that model that model inside the model predictive control algorithm, other than being fast, right? Because I can imagine if it is less accurate than the controller, that's not very useful, right?
Yeah, so here we come into the weak spot of these models. Of course, they are very fast. Of course, this comes at a price. There's a reason why other people are using all these like super computationally expensive models. These fast models are not always as accurate, and we have something we can call the model reality mismatch, right? So what we model in our simulation does not match exactly what's happening inside the plasma. But often for the purpose of control, we don't need to know exactly what's happening in the plasma because we use feedback control. So feedback control means that you adjust your controller signal that goes to the actuator based on the measurement that you take in real time. This is nothing new. This is something that has been applied since the beginning of tokamak. So for example, the early examples are like integrated quantities like plasma current. So you measure in real time the plasma current, you see it's too low, so you have to ramp up faster in your central solenoid. It's too high, you have to ramp up slower. So this is just feedback control with a proportional gain or whatever. There you don't even need a model. Then of course, what does the reduced model bring on the table? Like, how does this change the picture? Here, one thing is, of course, this model predictive control. And there, your question was basically, how good does this model have to be? Often, because you compare your output that you get with with your reference, you often get away with a model that is not perfect, because even, I mean, if the model just gives you like a direction to push your plasma in the right direction, you know, like it's this linearized dynamics tell you how you can best use your actuators to bring you back to the state. And even if it's not perfect, you will be corrected by the fact that you are using these real-time measurements and adjusting for example, in the case that your actuators are pushing the plasma away from what you want, you will get a bigger offset in your difference between the reference and what you wanted to achieve, and it will be able to correct for that. A second example I want to mention is that these models can also be used to tune our controllers. So basically, these models provide us with a digital twin of the tokamak, which we sometimes call the flight simulator. And instead of having like this long trial and error process where we try a controller on a plasma, then it doesn't work, we change the parameters a bit, we run the tokamak plasma again. This is, of course, this is something you can do on a tokamak on a university campus, where it doesn't matter if it disrupts from time to time because the energy confined is not so huge, so you're not destroying the tokamak and stuff like this. But of course, when we go to a reactor where the stored energy is enormous, where we need to have a reliable operation, there we don't want this kind of trial and error. And there, if we have a digital twin, like a tokamak in numeric space, let's say, and we can train the controller on this digital twin, we make a big gain, and we can like directly get a better performance of the controller when we actually apply it in the experiment.
Okay, yeah, that's actually an interesting point as well, because I mean, when we do sort of the experimental trial and error process, of course, there's more being learned than just, you know, how do we tune this controller, although that is definitely one thing that occurs. It's also, I suppose, in some way learning, well, how far off are we in terms of what we expected the plasma to do versus what it actually did. And I'm curious that inside this whole model predictive control paradigm, is there a way to get that information back out to say, okay, here your model deviated from your experiment significantly, and then we can feed that back to people who develop these models and say, okay, well, here's a place, here's a plasma or a condition that you probably want to look into, or figure out how to model better.
Yeah, this is actually something that that comes back to this process of state estimation, which I mentioned before. So it's basically by looking. So as I say, you have a prediction and you correct it with the measurements, and basically by looking into how much do I have to correct from my prediction to get the observation. This gives you a metric of how how good your model is performing, and you can even use the model parameters as the variables that are corrected by your Kalman filter procedure, and let the state estimator make changes directly to these variables to see how much do I need to change them to match the observed plasma state evolution. And then afterwards, of course, you can see and you can compare, like, okay, how much more did I have to increase turbulent transport? How much more was the radiation from the plasma compared to what I expect? Like, you can compare the observed quantities with the predicted quantities, basically.
Yeah, because I think there was, well, now I'm going to say something potentially stupid, but I think there was someone working in the US at the National Nation facility or something like that, where they were looking at sort of 2D distributions of like a beam deposition or something on like a plate, and they were able to use sort of these algorithms plus a bit of machine learning for the reconstruction, the image reconstruction, to self-calibrate the device, right? Because I guess the physics is a little bit more simple, that they kind of what they know their model is more or less perfect, and then they can say that, okay, if what we're seeing in the image is not what the model predicts, then we can while the beam is running, recalibrate everything to get the shape that we need.
That's really cool,
right? So do you think that we will ever hit something like that for the tokamak device?
Of course, you want to minimize the number of manual tuning coefficients. You want to like have the estimate correct itself and correct its own model parameters. I think so. The problem is always that it's not always transferable from one scenario to the next scenario. It's a tricky. There are a lot of hidden parameters when you're modeling a tokamak discharge, which are not obvious to all learn, by your observer. For example, a parameter which is often neglected is how clean your walls are, and if your predictive model like was learning, let's say, based on previous discharges where you had clean walls, and then all of a sudden the wall is more dirty, you get more impurity influx, you get more radiation, and so it's hard to be fully predictive, which is exactly why you need to learn on the fly, like you said, right? Why you need to adapt these parameters in during the simulation or during the real-time reconstruction. And of course, you can always get better in that. The question is, do we get good enough in this so that we can achieve the goals that we need to achieve to make fusion work, which is first avoid disruption. So can we know the state of the plasma well enough in real time so that we can avoid it from going towards disruptive boundaries where we know if it goes there in parameter space, we might lose control over the plasma. So that's the real aim, right? We don't need to get infinitely good. We need to be good enough, even for like not even for every scenario, right? Once we are going to a reactor, we can just have one, hopefully as boring as possible scenario where we achieve the aims that we need and where we can know the state of the plasma well enough that we can stay away from disruptive boundaries and technical limits where we know we can no longer, where we have no longer a handle over the plasma with the available actuators, things like this.
Yeah, that's also a very good point that you brought up, which is a big question for myself, because as you mentioned, once we move towards a real reactor technology, we'll probably have a standard scenario or standard plasma, right? That is just sort of, this is how we run our device. And in sort of my field where we're doing surrogate model generation, at the moment, we have to worry about a very large plasma parameter space because we want to capture all the different things that people might want to run their reactor in. Some maybe even some exotic shapes or exotic scenarios, because we're still in that development phase towards defining the standard. But do you think that at some point that when we hit the standard, actually a lot of the difficulties we have at the moment might disappear because we're kind of reduced our operational space to something that's a bit more manageable?
Yeah, partially, yes, I think so. I mean, current tokamaks are experimental devices where we want to test many different shapes of the plasma. How does the shape of the plasma affect the turbulence? We want to try, many different operating regimes because maybe we find, I mean, and often it happens that we find something interesting where we were not expecting it. A fusion reactor will not be an experimental device. We will, like you said, I think in that sense, yes, in the steady state of the machine, when it's at its maximal fusion power production during the discharge, you will have a relatively quiescent plasma where things might be, from the prediction point of view, easier than in current devices where you have to take into account all these fancy scenarios. Now, one more thing that you will still need to take into account is the transient phases. So you will still need to reach this operating point. So this is what we call the plasma ramp up. So it's called ramp up because it's the phase where we ramp up the plasma current at the beginning. So we have a breakdown at the beginning where we create the plasma at low temperatures, and then we start rising the current inside this plasma and start heating up this plasma column. And this phase is often tricky to optimize and to model, and is nevertheless very important because you need to reach the operating point where your performance is maximum. And it's not only that. So one thing is you want to make this phase as short as possible because you want to have as little as possible downtime. You want to, go there to your maximum operating point and sit there. But another point is because the dynamics are nonlinear, you might have some bifurcations there. If you, apply your actuators in a different order, you might end up at a different operating point. So there, I think things are a bit complex, but also there you could say once you have an optimized scenario, you just keep repeating it. And the second dynamic phase is the ram down phase, which is the opposite end of the discharge. When you want to end the discharge, you ram down the plasma current. This is a phase that on present tokamaks is often neglected because it's not so important whether or not the plasma disrupts during this phase, because on a present device, you're not destroying anything. Well, maybe there's an exception with the really big devices, but at least the tokamaks I'm used to work with there, people don't have to care so much about this ram down phase. But it's actually a very complex phase, and it's not only about routine operation, because you can also imagine the need for an emergency shutdown. So, for example, I can give an example. There is this phenomenon called detachment. So during operation, we need to radiate enough, like outside of, like in the mantle outside of the plasma, the scrape-off layer, so that the field lines, when the field lines actually hit the material surface, the temperature of the plasma there is low enough. Now, basically what can happen is that we lose the detachment at some point, and then we get attached to the wall. Now, when this happens, we get this huge heat flux on our diverter plates on the material surface of the wall. And then we need to ram down the plasma as fast as possible. Now, this is not so easy as it might seem, because you have this very hot plasma with an enormous plasma current, and in as little time as possible, you have to get the energy down and get the plasma current down. Now, one thing is, because the plasma is so hot, current diffusion is extremely slow. This is related to the magnetic field lines that are basically frozen inside the plasma once the temperature is very hot. If the plasma is very hot, it's an extremely good conductor, and this makes that the diffusion of field lines and the diffusion of currents is very slow. Now, I come back to something I mentioned before, which is the position control, the control of the vertical position of the plasma. I said that you need enough current by the edges of the plasma to maintain control over the vertical position of the plasma. Now, when you are ramping down a very hot plasma, it takes a lot of time to, drag the current out of the center towards the edges of the plasma. And the faster you ramp down, the more your current density becomes peaked, and the harder it gets to control the vertical position of the plasma. So that's an example where optimization is very important, and real-time estimation is very important, so that during the ramp down, you know what's happening. Because now this is one constraint that I mentioned, but at the same time, there are many other constraints playing. At the same time, you need to see that, for example, you don't get a radiative collapse of the plasma, that your heat that is radiated from the core does not exceed the heating of the plasma, things like this. This is extremely complex, and is something where you need a model that is good enough to optimize the scenario and to respond in real time and orchestrate the different control tasks.
Yeah, that's very, very interesting. So basically what you're saying is that if in these, let's just say, transient scenarios, that if you don't do it properly, you can actually make the situation worse.
Yeah,
right. So in trying to save the reactor, you might end up destroying the reactor because you did things in the wrong order.
And that's why you need a model that's good enough, so you can actually know, if you trigger these nonlinear dynamics, where does it go? Does it bring me towards a more stable situation, or does it? So that's I think these are phases where models are really important, and where we need to, even if on present devices maybe it's not so important, we can do the trial and error and etc. We need to make sure that the models we use are at least good enough to do this kind of exercises on the tokamaks we have now, so we have some confidence in these models, and so we know it can be done, so that when in the future we start operating these bigger tokamaks, we are ready with the tools that are needed to optimize and control them.
Yeah, that's you're right. I think because I've heard many people say that the world of control and the world of plasma modeling, like physics modeling, are quite separate, have been in the past quite separated, because sort of the control was, I don't want to say easier, but for the smaller machines, it was less catastrophic if you did it wrong.
Yeah, absolutely.
And in that way, they just said, okay, no matter what happens, we can always just adjust the controller gains and then it works.
Yeah.
But as you mentioned rightly, that as things get more complex and the consequences get more intense, then we have to bring these two worlds closer and closer together in order to get the right response. Hopefully the first time.
That's exactly right. Yeah, that's from the first time.
Yeah.
With as little a learning curve as possible. Yep, that's
All right. So, I mean, there's a fantastic conversation, but I do want to slowly ramp down, to use your terminology. But So let's just end on this note. So all of this stuff you mentioned, it's important for big machines such as ITER, but maybe we can sort of go through in a more systematic manner. Like, what does this mean for ITER? Like, why is it so important for ITER?
Yeah, so I can mention a few different points. So one of them I have already mentioned a few times. So we need to minimize the number of disruptions. We can not tolerate a large number of cases where, you know, the plasma with its full thermal energy, its full magnetic energy bumps into the wall. So we need to get our act together and be able to, from the first time, like know what the plasma is doing and how we are going to terminate it, things like this. Second point is ITER. Okay, ITER is still an experimental device, but future reactors, they are not experimental devices. They are envisioned to be power plants, right? And so they will have much less diagnostics compared to present devices. One actually one other reason for this is because they will need to maximize tritium breeding. So you will need to cover the wall of your vacuum vessel with lithium blankets so that you irradiate this lithium with the high energy neutrons from the plasma, which turn the lithium into tritium, which is fuel you need for your fusion reactions. And so you will not be able to have many diagnostics around the plasma, at least much less than in present devices. And this is exactly why these estimation techniques, where you combine scarce diagnostics with a model of the plasma to get an observed state, an optimal observed state of what's happening in the tokamak, is very important. And more important even on future devices than on present devices. And then I think the last point is just the fact that you will need to apply many different control tasks at the same time. So now on experimental devices, you can study one specific control task. You know, you choose a designated fraction of your discharge where you are going to study power exhaust control or NTM, like this tearing mode control or whatever. On a reactor, you will need to do all of that at the same time. And I think for this, it will be important that the controller that is supervising all of this, of where are we allocating our actuators, this controller will need to be aware of where in operation space are we and what happens if we move in this or in that direction our actuators. Where will this bring us? And so I think if you bring these aspects together, it becomes very clear that control on future devices will be very challenging, but also very interesting, and will need to be model aware, both for the real-time control and for the optimization in between discharges of like, yeah, to see how do we need to change things to optimize in the next discharge. But that's still more something you would do on a device like ITER, of course. Once you have a reactor, like we said before, hopefully you just have one scenario and you keep repeating it, I guess.
Yeah. No, and I think actually I just want to have an extra question since you just brought it up, is that as you mentioned, the future reactor will not have that many diagnostics in it for various reasons. But do you think even that these models or this environment of models that are being put together for this purpose can be used to help optimize which diagnostics are kept, like which ones are absolutely necessary?
I think that's a very interesting question. So I think based on the state estimators that we make, I think we can see how much information a certain diagnostic adds on the table, like how much it helps us to reduce. Because in the end, for example, when you use this Kalman filter, you don't only solve for the state of the plasma, but you also solve for the uncertainty on this state. And you can try turning on different diagnostics and see how much does that diagnostic help me to reduce the uncertainty on my estimated quantity. And of course, in an environment where your diagnostics are scarce, this is probably an exercise you will want to do, like how can I get the maximum out of the few diagnostics that I can install? Yeah, absolutely. I think that's a very good point.
Okay, super cool. And so I think with that, Simon, thanks for joining the podcast.
Was my pleasure.
Yeah, I learned
A
a
lot of
lot. And
fun to
honestly,
discuss this.
I could talk about this for much longer, but I think that we should wrap it up for sure. And so yeah, to all our listeners out there, thanks for joining again on this podcast. I hope you learned something new. There's a wide world out there in terms of both models and algorithms to play with, and it's a brand new future, as they say. So until next time, see you.
Bye.